Hello everyone. I'm going to talk about a method efficiently calculate 2D convolution with non-fused Winograd method on GPUs. Convolutional layers generally consume the bulk of the processing time. From Enjie thesis, they analyze the time distribution over different layers of CNN. In their case of doing image recognition, around 90% time is spent on convolutional layers. These layers are using general matrix-to-matrix multiplication, that's so-called GEMM method. Another paper conducted a comprehensive comparison of CNN implementations over a wide range of parameter configurations. In their performance profiling, GEMM operations take up more than 80% of total convolutional runtime. So we realized that convolutional computation is an important part of CNN. The Winograd algorithm reduces multiplications to 2 times less than the direct convolution. Especially with 3x3 filters, the non-fused Winograd methods are fastest in most cases from the paper mentioned. There remains a challenge to efficiently implement Winograd convolution on GPUs to deliver the full speedup as promised in theory. We believe software techniques are required to address challenges, such as the efficiency of data transfers, data reusability issues, and the managing of limited resources. The 2D Winograd method could be implemented by 4 steps to convert filter, convert tile, dot product, and convert result tile. Fused methods reduce data transfer significantly, but step 2 results cannot be used by multiple filters. The non-fused methods calculate each step in an independent GPU kernel. More registers used could result in register spilling, which lower occupancy. This paper presents an optimized implementation for Winograd non-fused convolution. I will introduce these 4 steps in order. The first step is to convert filter. The first step is to convert filter by matrix G. Compared with the input data, the filter data is relatively small in size, though with same number of channels. Despite that, this step contributes only a small percentage to the total performance. The storing method and the access pattern could make huge influence to the step 3, the dot product step, because each input type needs to perform a dot product with all filter types. Since matrix G is small in size and very simple, thus the 2-pair matrix multiplications can be expanded to additions and only 12 multiplications. Benefiting from this computational simplification, each thread can calculate one result fx independently from other threads without waiting for synchronization. Utilize this simplification, each thread can be mapped directly to one output, improving efficiency of threads in a warp, calculating the same fx using the same formula but with different filter inputs. In this figure, for example, threads in warp 0 are all responsible for calculating element f0. And the first threads in all 16 warps are all responsible for calculating filter 0. In this way, warp threads execute the same instruction set concurrently to avoid thread divergence. When saving the filter data in the shared memory, if we put the same indexed elements from different tags in the same column, threads in the same warp need to access addresses in the same bank, which may lead to serious bank conflicts. The problem still exists at the calculation stage. Elements of the input filter are used multiple times. As shared memory space in this step is not a limited resource, to solve the problem, the extra 16 columns of shared memory are used for padding to reduce bank conflicts. When the calculation finishes, the result is stored in 1D texture memory in a tile united CHWN layout to help loading in step 3. The second step of the 2D Winograd method is to convert tiles. Tiles are extracted from the original input. With Winograd, tile extraction is different from direct convolution with a given thread. For example, when thread is 1, the direct convolution slides a filter through each tile on a feature map by one element, while the Winograd method slides filter by 2 elements. The Winograd method says the thread is R-1, but we found it is not all the cases. We summarize some direct convolution thread T and Winograd tile thread WT in this table. We can see WT thread could be bigger than R, where R is the filter size. That means less tiles extracted result with less computation and less memory. This is important for improving hardware resources efficiency and performance. Then the second step is to convert tiles. The thread data mapping for this step we used is one thread responsible for one element, loading and calculation. This step can be split into 2 tasks. Task A is to load the original layout input. Layout is an CHW input feature map into the first shared memory. Task B is to expand each tile from overlap and calculate AIG from task A and store intermediate results to the second shared memory. Task C to calculate BIG from B and store result back to the second shared memory. Task D is to output result to devices for the next step. For traditional data parallel model, these 4 steps are serialized because all the threads in a block all execute the same program over independent elements from arrays of input data. On the hardware, however, a thread block is broken into warps consisting of 32 threads, which serve as a unit of scheduling. Warp specialization divides threads of a block into warps. In partition, computations into subcomputations, such that each subcomputation is executed by a different warp within a thread block. So that threads within a warp have good data parallel behavior, even if threads in different warps do not. data parallel synchronization is performed using barriers between all the threads within a block. However, by using inline PTX statements, we only synchronize related verbs in a block. Verb specialization allows subsets of threads within a block to have their behavior tuned for a particular purpose, which enables more efficient consumption of constrained resources. To prevent the verb's execution from being blocked by too many synchronization instructions, grouped producer-consumer chains using named barriers in PTX are designed to reduce synchronization and achieve data safety. By assigning individual verbs a different task, we can use verb specialized program to separate memory operations from arithmetic. To ensure these tasks run in parallel with properly synchronized data, 4 producer-consumer chains or iterations are used for the calculation of the 10-row data in the whole block. Here we use 2 named barriers to coordinate movement of data from a producer verb, red, to a consumer verb, blue, through 2 buffers in shared memory. Before each chain starts, task A has already been completed in previous iteration or initialization. Consequently, in the consumer verb groups, the first task executing before named barrier 0 is task B. When the producer verb groups calling bar.synchro, they block and wait at the named barrier 0 until the consumer has called bar.arrive, which informs all producers that task B is ready and it is safe to write new data in. Task A does not depend on any other tasks, and task B in the same iteration does not depend on task A either. The producer starts working on task A and C as soon as the named barrier 0 receives the signal from consumer. Then it emits a signal after finishing task A and C by named barrier 1 with a bar arrived instruction. Then task D in consumer knows task C has finished and the data is ready for output. At the point task A for the next iteration is already ready. As task D is not followed by other tasks, the producer and the consumer end their relationship, and 2 named barriers are safe recycled for reuse in the next iteration, as they are limited resources. The third step is to calculate the dot product between converted filters and tiles. Then we arrived to calculate the dot product. This needs to calculate the element-wise multiplications between each channel of the converted filters and tiles, then to collapse the tile over C channels down to a single channel. We assume the number of channels is multiple of 8, with a 32 by 32 thread block, one thread calculating only one output. Each block can handle 8 channels of data loading and calculation in each outer iteration. Threads in the block corporately loading necessary data from off-chip global memory to on-chip shared memory, then reuse this data by shared memory. In inner iteration, one thread block responsible for calculating 8 tiles of input and 8 tiles of filter. As calculation in each channel is independent from each other, prefetching can hide the long data transfer latency. The global memory latency is about 100 times of that of shared memory operations. It is important to hide the latency. Unlike GEMM, calculations start after all threads in the block finish loading. We utilize software prefetching in this step to hide the memory latency caused by the movement of big amount of data. All threads in a block can start calculating even with only one channel data. That means 8 types of input and 8 types of filter. Double buffering we used here is to ensure the computing threads always have available data to compute on one of the two buffers. The last step is to convert resulttile. In the last step, one thread is mapped to calculate a one-tile generating 4-element outputs, and the calculation is simplified to additions by unfolding multiplication of two matrices. Because matrix A only contains ones and zeros, each thread has calculated 4 outputs. But direct output cannot achieve coalescing because continuous threads access thread address. Using shared memory is a normal way, but big chunk of extra shared memory can be a limiter which lower occupancy. Instead, shuffle is a way of exchange data in a warp, but which any thread can read other threads registers in the same warp. Then we apply a shuffle up to pass one values of each thread in the first half warp to threads in the second half warp, then followed by cross-accessing to output continuous 32 elements by one warp thread to achieve coalescing access. This figure focuses on outputting results calculated by the first half warp threads. This figure only shows one instruction for the first line read results. These half warp threads produce 2 by 32 results, which need 2 shuffle up instructions to output these results by leveraging the second half warp threads. Our evaluation is done by the most popular 3x3 filter size, one as thread value and with NCHW as data layout for input and output. That is the same as QDNN. Parameters used for evaluation include batch size, width, number of filters, and number of channels. To evaluate a first step convert filter, we use parameters 1 to 1 to x to 16, where x indicates the number of filters in this case, and the value range from 8 to 256. Batch and width do not contribute to filter number and attended results, so they are set to 1. We use dual y-axis to show y values to better illustrate a tiny difference. Values shown in lines are measured by the right y-axis, while those in columns are measured by the left. In the 12 comparisons shown in the figure, our method shows significant improvements over QDN Winograd non-fused method in 9 comparisons, and only 3 shows insignificant improvements, like filter number in chart 3, batch size in chart D, and channel number in chart B. In general, our method achieves a speed up of 1.64 times in total, benefiting from fully coalescing, data reuse, efficient thread data mapping, and reducing bound conflicts, and warp specialized program.